Well, we've learned about SN2 and SN1, and now we've learned that there's another reaction called E2. And you might have noticed that bases are also nucleophiles. So when you're looking at one of these reactions, you might think, well, is the base going to act as a base or is it going to act as a nucleophile? Let's look and see how you determine what happens in any particular circumstance. Okay, if I look at E2, and E2 reaction is going to be favored by a strong base, that means that a weak base is going to favor SN2. Because if it's a strong base, when it comes in to do nucleophilic attack, what's going to happen? It's going to grab a proton instead of attacking the carbon. But if it's a weak base, it's going to be pretty weak at pulling a proton off, and instead it's going to favor the nucleophilic attack. So if you have a primary carbon, SN2 is very fast. And even if it's a strong base, SN2 is so fast, you usually have the SN2 reaction predominate. The exception is if you use this base right here. This is called T-butoxide. And T-butoxide is a T-butyl group on an oxygen, and then, of course, it's a base because it's negative here and positive there. It's a T-butanol that's been changed into the conjugate base. The T-butyl group is really, really bulky. So when it tries to do an SN2 on the carbon, the T-butyl group is so bulky, it won't allow an SN2 to occur. So if you have T-butoxide as a base in any reaction, you just automatically are going to say E2 is going to occur. Otherwise, pretty much every nucleophile will do SN2. If you have a secondary carbon, though, SN2 is slower. And so only if the nucleophile is not a strong base will SN2 occur. If it's a strong base, even if it's not T-butoxide, let's say it's sodium ethoxide or potassium hydroxide, those are going to end up doing E2 on that carbon if it's secondary. Sometimes we want to make sure that E2 goes ahead, so we just use T-butoxide anyhow. And when we don't want elimination to go ahead, we have to choose carefully not to have a basic. So this is the relative basicity of nucleophiles. Over here, these are very strong bases. And so on secondary carbons, they're going to cause E2 to occur. On a primary carbon, most likely they'll do SN2. However, over here, these are very non-basic. The non-basic nucleophiles are going to do SN2 on a secondary carbon, and they're unlikely to cause any elimination. In the middle right here, these primarily cause SN2 on primary and secondary. There's probably a little tiny bit of E2 is going to occur, but the SN2 reaction is going to predominate. Okay, so here we go. How are we going to determine what occurs? This is a secondary carbon, so now we say, is it going to be SN1, SN2, or E2? Let's look at the conditions. If I look at the conditions, we're not going to have SN1. It's a base. And remember, I told you earlier that SN1 only occurs when you have a non-basic nucleophile. So if I look at this, I see this is a strong base. It's secondary, elimination is going to occur. But if I look down here, SN1 is not going to occur because we have DMF as a solvent and a good nucleophile. That's SN2 conditions. This good nucleophile is a weak base, so the major product is going to be SN2. Don't forget, this is a very strong base. Don't forget, sodium cyanide, sodium thiolate, sodium chloride, all those are weak bases. You go ahead and try these two problems. Okay, if I look at this, I see that this is a secondary carbon, and I see a hindered base. That bulky base, that's going to cause elimination. So what do I get? I get the most substituted alkene. What about over here? This is a primary halide. I've got a very basic nucleophile, but it's primary, and I'm in a good SN2 solvent, DMF. Primarily SN2 is going to be occurring. And so what do we get? We get this ether forming. Would there be any E2 product? Probably there would be some, but the major product would be the SN2. There is something called the kinetic isotope effect. Let's look at deuterium. Deuterium is just a hydrogen atom with a neutron in there. Hydrogen is considered to have no neutrons because the majority of them do not. So when we write H, we're just saying hydrogen with no neutrons. Because of the greater mass of deuterium, the carbon-deuterium bond is stronger than the carbon-hydrogen bond. That stronger bond makes it slower to break. As a result, it's less likely to be removed by a base in E2 because it slows that reaction rate with the stronger bond. When we look at this, this tells us that the carbon-hydrogen bond is being broken in the transition state. So the slower E2 reaction rate is evidence that the carbon-hydrogen or the carbon-deuterium bond is being broken in the transition state. But this is my point of introducing to you deuterium having a stronger bond. Realize that this is important because there's times that you might be tested on remembering that the carbon-deuterium bond is stronger. So if you have two options and they're identical except that one is deuterium and one is hydrogen, the carbon-hydrogen bond is more likely to